All right, thank you so much. So to contextualize the recording when people rewatch this, so we're going to discuss a little bit surrounding the parser extraction, so getting the shortest paths. So Wafa is going to lead with her progress on that, things that have been preventing any sort of movement on that issue, and we'll talk about code modularity as well for those that want to discuss the repo structure, the way they are setting things up. And then we can segue into how you would then take that repo structure and interact with our cloud portal. And the webinar for that is coming soon. And at the back half of this meeting, Debelina, if you're still on, you might be able to talk a little bit about the scheduling of that, because that is going to be an exciting turning point here where we can scale out. And this also coincides with the Dask pre-recorded materials, which I have sent a link to you and Sarah, but literally 5 minutes ago. So you may not have got to see that yet, but everybody on this call will be able to watch that very shortly. And you will be able to see how you can begin porting your repo structure into a Dask graph, which will allow you to parallelize and scale out your data operations for all of the PubMed abstracts. So that's the agenda for today. And then as questions come up, again, please feel free to ask either audio or chat. But Wafa, why don't you start? And we can take a look at what's been going on with your parsing extraction and what the next steps might be for that.
Colin, sorry to interrupt. Wafa, if you don't mind giving me a few minutes, I do have to drop out soon. So if we can just talk about the AWS part right away.
Yeah, of course.
Okay,
of course.
yeah, sure.
Thanks, Wafa. So everything, the data science portal is up and ready, but before you guys use it, you have to look at the training material, which Colin has it ready, and we'll put it on the site today. Some of the questions I had, and Colin, you can help me over here, is I was thinking of one account per team. Would the teams be okay with that? So you'd have to kind of timeshare the account that is given to you. Colin, do you see any difficulty in that if they have to? So let's say when they are using the Dask, for example, they would have to make sure that they're not conflicting with the other guys in their own team.
Yeah, I think that makes sense. One account per team. And I think also watching kind of Jillian's webinar plus my Dask webinar will help you see, for the teams or participants on the call today, see exactly how you would submit jobs. Again, the workflow is going to be localized so that on your individual laptops, each one of you is going to verify that your pipeline works, and you can help build that pipeline. And then there'll be one submitter per team, basically, that is kind of taking the charge on scaling out the operation using the cluster. And I think that's going to be straightforward. So I don't see any conflicts in terms of actually submitting things. Like, I don't think that will be a problem at all.
All right, awesome. So we'll have one for each of the session 1 teams, and the session 2 teams, we'll just give you an early one, even though you are kind of not yet there. So just because you have access to all the material, if you want to try out, you can just get started on that as well. So we'll do one for each of the 4 June teams and one for the end June or July team that came in. Other question that I had was, is everyone at the same spot? I'm sure, like that. I mean, or rather, let me answer the question. I know that everyone is not in the same spot as far as the coding goes, and it is part. There was a question raised as to why there is so much difference in skills coming in, and that is part of the. It is the essence of this program that each one of your teams, they have a gradation of skills. So the ones who are more experienced, you are getting to learn directly from Colin, but you're helping the others as well. That is the essence of it. But in the showcasing, we do want to make sure that whatever you have done is reflected accurately in one is your self-assessments, why that is so important, because that says exactly what you have done. But we also want a way of kind of, when you run this code or when you're creating this code in your GitHub, like the common GitHub that you have, to have the contributors mentioned very specifically over there. So I just wanted to take a moment to see how the teams are doing it and whether you're on the correct path on this. So Wafa, for example, in your team, is there some way that you're seeing who is contributing what, or for the people who are struggling, we still want it to be a great experience for everyone. Is there a way that you can simplify it? So this is the part that Colin, I was discussing with you yesterday, is for, we want everyone to have the full experience of the project. So at this point, you're deep in, so you really know where you're at. So there are ways that, we can give you some checkpoints and you can work on, so that you don't get into a rut on one specific problem. You can progress beyond that and continue the rest of the project. Does that make sense? Colin, or do you mind explaining it a little bit more?
Yeah, absolutely. I completely agree with that sentiment. So we don't want to get bogged down in engineering challenges and have that define the total experience. So as I predicted, and this is definitely the case when I was trying to design these elements, right? The parsing can be really challenging from an engineering standpoint, and getting the input data for the machine learning can be a huge challenge. This is reflective of reality when these are often where the bottlenecks occur, is sourcing and procuring data. But we also don't want that to be kind of the domineering aspect of this. So I think that an alternative that might make sense, and we can discuss it all together to see how you guys feel, is by simply taking the clean dependency path matrix that is provided by the authors. We can then use that data and move forward. And that way you have part of the experience of trying to source that data. But if it's proving to be so challenging that it's impossible to get that data in one place, then we can move ahead with that kind of pre-processed, curated data set that they provide. And that way the focus from here on out could be more on the machine learning and interpretation, because I really think that's where you can come away with lots of great lessons in addition to the engineering, is in the interpretation aspect of this, right? So actually running that machine learning, talking through that, and then as a capstone, describing the end-to-end process, and then just trying to analyze how all of these pieces fit together is, I think, one of the main takeaways. And so what we don't want to do is preclude any one team or participant from getting to experience parts of those things. So I think that that's the most straightforward way. And I think that that's probably the unanimous, bet for the hardest piece of this so far, and probably the entire thing, is actually getting the final shortest path from the dependency matrices, which I know, Wafa, we were about to talk about. But does that seem reasonable? Definitely, I don't know if you also want to build on that, or other teams. Does that seem like a good approach for those who are really struggling to source the input to EBC?
It sounds like a good idea to me. If you're saying that that first part is the engineering, it is a nice way of differentiating it also. Like there is the machine learning algorithms coming up, and this is the engineering aspect of it. So anyone who has already completed that, everyone is trying it. That is, we have all of you here. But as to whether you're completing it or not, that might be a good way to differentiate it.
Yeah, I agree. I think at this point, if it's still very challenging to build a local pipeline that works, and by local, I mean one of those XML files and extracting the relevant sentences and paths within, then like Debolina is saying, that's a good differentiator, so that teams that want to move forward and tackle both the engineering and interpretation aspects can do so. And then teams that really are feeling like this is, again, beginning to dominate all of their discussions and they can't push through that bottleneck, they can have the data that's already cleaned and curated, and they can, reflect on what had to go in to get that for the authors. And hopefully this was a good experience, seeing the amount of things that go into creating data like this, because again, that's part of the realism of this project, is in these large scope research questions, or even in industry, these are the kinds of problems you will have to face all the time. So you want to be able to get experience with them, but you also don't want to have that define the entire takeaway here. So yeah, I think that at this point, being at the amount of weeks we're in, I think that that would be a good way to make sure everybody is pushing forward and feeling like they're getting more out of it, learning new things, as opposed to just staying stuck on one very particular finicky aspect of the engineering. Because I do know some teams are basically already done with that piece. There's a little bit of validation, but they have completed the overall pipeline. But then other teams still don't have a robust way of getting those dependency paths in general. So it'd be great to hear from other teams. And, Devlin, it might make sense now to segue into Wafa, what you think about this, and what your team feels about that potential approach. Or if you want to keep pushing on with this, because you might be right on the brink of figuring this out, and maybe, it's just a few details that you need to sort out, and we can help with that. Or that might seem like a really reasonable way to get everybody, you and your team, back on track and pushing towards something new, as opposed to staying stuck on the same engineering task.
Right. And it doesn't have to be on a team basis, the distinction. So Wafa, in your team, it's possible that a few people are comfortable with it and you can make it as team leads, all the team leads, not just Wafa, you can make the distinction between anyone who is really struggling, they've learned it, but they can move on to the next step. So Wafa, all yours. Let us know what you're thinking.
Okay. So what I want to say is in our team, we kind of divided ourselves into subgroups. So we have a subgroup working on the engineering part or the pre-processing part, and we have a subgroup working on the actual machine learning algorithm, so the EVC code. And we also have a subgroup that's working on Dask and AWS and figuring out how are we going to process the entire database. So it's kind of like we tried to move forward in the 3 tasks in parallel so as not to get stuck in one task. Mm-hmm. But yeah, regarding the pre-processing or the engineering, we still have some questions. I don't know if it's going to be very challenging to solve it, but yeah, it can be a choice that we can use the pre-existing database and move forward, but we can still work on that.
Yeah, and I don't want to interrupt Wafa. That's great to hear the context. The other thing I would just build before you continue is that for those of your participants and if you guys are working on part of the pre-processing, you can move forward with the author's data and still keep building out your own pre-processing pipeline. It's just that pre-processing pipeline might not be used to get the final results. But this way, everybody that's invested this time and energy in trying to construct that can keep refining and iterating, even if they can't actually materialize the results. And by this, I mean, going a little further than pseudocode, you can continue to work with Jython, you can continue to work with the tools and libraries available to try and get the parsing, because I do believe this is a really excellent highlight in an interview situation to talk about this problem and to talk about kind of how you've been thinking deeply about the engineering aspects and the approaches. So for those of your team members that have actually been working on that code, I would recommend, even if you want to move forward with the author's data set, still keep building out the code that you have, still keep tinkering, because even if the final product of your team is revolving around the original data set from the authors, you can still highlight your contributions, even if, again, it's not part of your final results. So I definitely don't want to discourage or dissuade people working on the pre-processing from iterating further. It's just you might be able to push forward as a group without the pressure of having to get that data to try and execute your tasks, if that makes sense. So please continue. I didn't want to interrupt, but thank you for that, Wafa.
Okay, yeah, that sounds good. So regarding the dependency extraction, what we are stuck in now is, okay, first of all, we use the Stanford parser in Jython implementation. So our plan is to take a sentence and that we already know that contains a drug and the gene, and we know the location of the drug and the gene. So we use the function that can extract the least common node of the drug and gene. And we also have a function that can extract the path connecting the drug and gene. But the problem is that we are not able to construct the dependency path or the dependency matrix the same way that's presented in the paper, because the relations that are extracted using the parser are not in the same way as the tree structure that's presented in the paper.
And can you show the contrast between what the paper outputs and what your current pipeline outputs? Because are you using the sentence that basically forms the figure with kind of the core sentence at the top, then there's parts B and C that have the tree structure, and then part D is the bracketed expression of the dependency path. Is that the sentence you're trying to parse?
Yes.
Okay, cool. Would you mind showing, if you have it readily available, the difference between what they output as the path and what you currently are outputting as the path?
Okay, yeah. Can I share my screen? Do I
I
have the...
believe so. I don't know if I am allowed to give you permission if you don't have it.
Yeah, I can share my screen.
Okay, great.
Okay, can you see it now?
Yes.
Okay, so this is the sentence. And this is the least common node for the drug and gene is increased. And this is the path that's connecting them. So, and this is also the dependency relations between each pair of words in the sentence. So, as you can see from the matrix that's in the paper, they have, for example, between exposure and between this name, there is a relation that's NN. Okay, we have this one. Then we have between exposure and increased, there should be a relation of agent, which is not here. I have between increased and expression, this one is present, and this one is also present. So basically, I wasn't able to construct the relation between increased and exposure, which is the way to complete like the total pass.
Okay, yeah, thank you so much for showing this. This is super helpful. And do you have readily available what the sort of gold standard that we're trying to replicate is next to this so that other people on the call can see them side by side? Just the figure, I forget what figure number it is, but the one that actually has the bracketed expression.
Okay, I need to stop sharing and share again.
Okay, thank you. Appreciate it.
Okay, this is it.
Great.
So this relation I wasn't able to extract.
Okay, yeah, so this is tough to debug. It's tough to know if this is something you need to debug. So the reason why, right, is that they are taking this sentence and they're taking a version of the Stanford parser that we don't necessarily have the exact version of. So you remember with parsers, there's no stochasticity after they have been trained, but there are a lot of different versions of parsers floating around. So one potential area that might create the delta between what we're seeing here and what your output is they're just simply using a slightly different version of the parser. Maybe it's more up to date or less up to date than ours. I think that because you are correctly extracting a relation between drug and gene. So if we go back to your output, sorry for making you go back and forth.
Maybe I should just share everything.
Yeah, you don't feel like you. Yeah, don't feel like you have to though if you don't want to share.
No, it's fine.
Okay, cool. Great. So here we at least see inhibited as the correct join between these two, right? So this path that you're extracting, the clonidine inhibit acetylcholinesterase activity, the least common node, and okay, so okay, we're going on this one. Okay, expression increase. Okay, so we have two sentences going. Yeah, let's just look at this one, right? So this is still correctly linking, right, clonidine to acetylcholinesterase. The linking word is still correct. So one thing that we can do is this isn't necessarily wrong. It's just descriptive in a different way, right, than what their tree structure portrays. But the core relationship is still reflected in the dependency parts that you're getting here, right? So inhibition is the core linkage between the two. And inhibition is also one of the cluster labels, right, if you remember from the dendrogram. So the most important piece of information in this sentence is that clonidine is inhibiting acetylcholinesterase activity. That's the critical idea in this sentence. And that's what your least common node and path is actually reflecting here, right? When you print this out. So this isn't necessarily wrong. It's just giving you a different degree of granularity in description. And what I would say is they make this point in their paper, right? If, first of all, there's no gold standard ground truth for a dependency parse necessarily. It's just its best guess at what's coming out of it. So this isn't necessarily wrong. And if you consistently predict sentences like this in the same way, they make an equivalent point in the 2015 paper saying inconsistencies, as long as you're getting things wrong in the same way, that's fine, right? Because you're still looking for the relationships. And if you're able to extract the relationships via this process that you're showing here, that's fine, as long as it's doing it in a stable way. So if you got an equivalent sentence with a different drug and gene name with the same linkage of inhibited, right? If it said non-competitively inhibited, if it was still able to extract this path, that would be fine. So what I would say is, again, this isn't necessarily wrong at all. You're still correctly linking the drug and gene. It's just not exactly the same as the way they have it. Now, again, we were trying to replicate, but that's okay. You know, it's impossible to get every single detail lined up perfectly. I think the fact that you're extracting the core relationship here means that you're still on the right track, right? You're still able to take this. And if you were to generalize this process across all abstracts, you would still be able to learn something useful because you're still discovering that clonidine and acetylcholinesterase are linked in some way, and they're linked via this word inhibited. This is the core defining relationship between these two words. So yeah, you know, I think that that's totally fine. And in fact, given what you're showing me here, it would even be very interesting to see when you take their matrix, right, the original author's matrix, and compare it to the matrix you will produce with this code, what are the final differences? If there are minimal differences, then you're in the clear. If there are differences, it still doesn't mean you're wrong. It just might mean that you were extracting information in a slightly different way because maybe your parser version was different. So I think that's the most reasonable explanation, is there might be slight version asymmetry between what they used and what we use. And because they don't provide, for example, a Docker image with the exact software stack they used, we're never going to be able to completely get this right unless we were contacting the authors themselves and said, can you give me the exact, you know, software dependencies that we need? So you don't feel like this is a mistake on your part or a bug you need to fix. I think this is just, you know, an alternative way of getting the same information. And ultimately this would converge to something useful when you would put this through EDC. Does that make sense?
Yeah, it does.
Great. So yeah, and if you're finding that you're seeing inconsistencies, and by inconsistencies, I mean, for example, if your process did not recover the word inhibited as the linkage between clonidine and acetylcholinesterase, then you would be concerned, right? Because if you couldn't discover that that was the path, or at least the core part of the path, that means that your parse is actually just wrong. So your parse is taking a more limited set of relationships, or it's kind of materializing the tree path in a slightly different way, but the information it's conveying, the critical piece, is identical to what the original paper had. What you really want to watch out for is if inhibited was not discovered to be the linkage between the two, and if those weren't flagged as drugs and genes in general. That's where you start to be concerned. Are we flagging this properly? Are we instantiating the parser properly? Here it looks like you're doing both of those things completely correctly. It's just giving you slightly different answers. And that's not necessarily a bad thing at all.
Okay, that sounds good.
Cool.
So I have just more questions. Can I ask them?
Of course. Yep.
Okay, there is also a question about the lists of the drug and gene names that we are supposed to use. Because we found lots of lists in DrugBank and in PharmDKB, and we're not sure which one exactly are we supposed to use.
Well, on this topic, I would say, again, there's no gold standard answer because these lists themselves are kind of curated by human beings. So I think that if you have an exhaustive list of drugs, one thing you can do is intersect, right? You can take whatever the consensus is across, or you could create a union, right? And just say, I want to err on the side of sensitivity, which means that for all of the lists you have, just take the set or union operation across all of them and just get every possible drug name. I would stick with the UniProt database for now if you don't already have a gene list. That's curated, that's easy to use. And correct me if I'm wrong, hopefully somebody on this call has already been using the UniProt genes and part of their pipeline, but that should be relatively straightforward. The drug list, like you're saying, multiple different data sources that you could construct that from. I think that, again, there's no right or wrong answer, but you might want to err on the side of sensitivity by taking as many as possible. That's what when people say err on the side of sensitivity, they mean, just try and catch as many things as possible, because odds are if it's in one of those lists, it's a real drug. Very rarely do, non-consensus drugs get put in those databases. I don't think it's possible even. So if you find multiple different sets of drugs, simply take, the union across all of them and just get the unique elements and treat that as your list. If there's not one sort of set data element you want to work with. Does that help answer that question?
Yeah, that sounds good.
Great.
Okay, if anyone else in the team, I guess some members are present. If you have any more questions, can you just ask them?
So the video about AWS and Dask is up right now, or?
So it's about to be. Sorry for the delay on this. I had sent the Google Drive link, so based on the file size, it might take a couple minutes to upload. It should be there very shortly. Either Sarah or Debelina will get that up there. And just to be clear, I'll just frame it. That's bringing it up. Essentially, I'm demoing Dask on my laptop, as this is the way you will construct your Dask pipelines. Then very shortly, there's going to be a webinar on the AWS portal. And it's going to be very straightforward to take your local code that was developed on your laptop. Then you will commit it to Git. Then you can pull in that code in AWS pretty easily. And in this sense, everything should, I hate saying just work, but it should just work in the sense that Dask is already pre-installed on the Docker image that fuels our AWS instance. So hopefully there are very few software requirements and compatibilities, but that's what I would say is that step is, you kind of have to port code that you develop locally onto AWS, unless you want to write your entire pipeline using the AWS and JupyterLab instance, which I would recommend against doing personally. That's my bias, is I like to develop in VS Code on my laptop and then kind of port or ship my code to other places to execute. So that's the pattern I use, but you can also directly develop this code or pipeline in JupyterLab itself with the AWS cluster. So yeah, that's something to keep in mind. Is my tutorial is talking about Dask. It's going to orient you towards it. It's also going to orient you as to how to construct the pipeline to be able to run on AWS. And then Jillian, our actual DevOps engineer, will show you operationally how you get in and launch a notebook and actually pull things in from Git. She'll cover those topics when she gives that webinar.
Okay, thank you.
Yep, absolutely. Good question. Cool. So any other questions on those topics? I know we had one question about modularity and repo structure, and I don't know who. Oh yeah, was that you?
Yeah. So
Awesome.
actually, I'm from the other group, and I was the one who posted that question.
Great.
If if there's some time, my group also prepared a presentation, but of our progress and like our bottlenecks. But if we don't have time, we can go straight into the modularity, because we have a very similar issue as the group that just presented.
Okay.
Or like it's just a different. I guess we just took it a different approach to the problem, and we have a slightly different technical issue.
Okay, that's fantastic to hear. So before I let Matthew present that and talk about that, is there anybody that has other questions before we move into that I can address?
Hello, Colin.
Hey.
Would you mind to share the pipeline for pre-processing? I mean, the exact coding.
Sorry, so you're saying you want to share yours and talk about it, or?
No, I was thinking if you can share the exact coding for pre-processing.
So the way that I've been doing it, so I don't have an exact programmatic recipe for the pre-processing. So each team has their own. So there's no kind of recipe to share. If we want to talk about yours, time permitting, we can also look at yours and I can tell you kind of how I would construct each piece, but there's no singular file that I can share with you.
Okay, because I was wondering, are we going to use the same pipeline or are we going to use our own ones?
I think the goal is for everybody to create their own, and that's also an interesting exploration into differences of how multiple different pipelines can produce either the same or differing answers. So that's part of, I think, the strength of this approach is, often seeing how multiple people can arrive at the same answer. It's a good kind of validation or QC check to ensure that things are moving kind of consistently. But yeah, I would focus on your own. And then again, if there's some aspect of the pipeline that is a true bottleneck where it's preventing you from actually doing the machine learning in some way, then we can kind of fill in the gaps by just taking the author's original data, and you can continue to develop your code that actually does the preprocessing pipeline, because that's something I guarantee you're going to want to be able to talk about in an interview situation, is how you set that up, why you set it up the way you did. But then you can also use the author's data so that you can push forward and finish the machine learning portions.
I see. Okay, thank you.
No problem. Okay, awesome. So Matthew, without further ado, if you want to present whatever you have, and love to hear it and just kind of give you any feedback that I can.
Okay, thank you. Can you see my screen? Can everybody? Yes. Okay, cool. So I'll make this quick. So so I just want to present our pipeline for our group. It might be slightly differing, but I think for the most part, it's very similar to what the other group did. So for we finished 3 modules so far, but like we're having issues in the 3rd module, which I highlighted red over here. But just a quick so we took the raw data, blah blah blah, and then we removed duplicates after we got the usable sentences, after we matched it with PubMed. And we got 2,000 usable sentences. And when we input it into the Stanford parser, we got 3 types of outputs, because for my group, we actually just used the Java implementation. But I think part of like my group rewatched your presentation. I think it was like yesterday or like sometime this week, and we realized that the Jython implementation might have some signals that are not present in purely just the Java implementation, and it might be useful for us to merge the two of the Jython and the Java outputs to actually create the dependency parse. So that's actually something that we want to do as well really shortly. And for module 2, the output we got was a dependency path matrix. We just took the Stanford parser output. We just took the type dependency, so we ignored the pen and word and tags. I'm not sure if because I think most of the information we found in the type dependencies, but you can correct us if like we're doing something wrong as well. And then we got a dependency path matrix, which is here. So this is the sparse matrix that we got, but I'm also realizing for module 3, we used matrix.py in order, I'm presuming that we should use this script, and there's a read data function in this particular script that we pulled from the repo of the EBZ algorithm implementation, and the input requires so the input required for this is in this format as we understand it. It was from feature 1 to feature n, and so how we might plug it in is something like this. And I think this is why this was like important. So my suspicion, or like our group's suspicion, is that we need the data to be in the format of D over here. And only this will be able to be ingested by the Stanford parser. I mean, sorry, not the Stanford parser, the EBC algorithm. That read data function in that matrix.py script. So I looked through a few of the script, and I'm just not sure which. So like I think the biggest bet is that read data function to be put in. And that's kind of like what we are trying to do over here. Use that sparse matrix and okay. And so our bottleneck right now is to be able to actually, like the other group got tested it on this sentence and it worked, but we're not sure how to get this, because our current output right now is this kind of like matrix where the rows are just indicator variables of its presence or not, or if it's not, or its absence. So like, yeah, I think we're just stuck at trying to get this parse, is like if whether or not this is directly from the Stanford parser output, we are not too sure, because yeah, sorry for jumping around here and there, but like but the outputs were these three things that we looked for. Yeah, so that sums up what we have. We basically tried to use this output to in what we did, and we applied it to all the 2000 sentences we have.
Cool. Well, the first piece of feedback is this is an absolutely fantastic way of getting me oriented about your bottleneck. So this is just, you guys did a great job of explaining what's going on, what you're trying to do, what you have done. So, very commendable in structuring this, because it's not easy to do. I really like the diagram approach that you take that breaks down kind of the flow over time. You kind of have an implicit time axis going on there. And I like that a lot, just kind of showing how things have progressed. So the one thing I would say is, can we scroll back down to your matrix that you currently have? The dependency matrix right here. So one thing I would say is, are these column names, are they just getting cut off, or so like A mod, the first column?
Yeah, I have the full matrix over here.
Okay.
Yep. This yeah, so like I think VS Code is helpful here. It's just the coloring is a column. Yeah.
Yeah. So it seems like for some of it's tough without having seen the process, but they don't seem like complete dependency paths, right?
Right.
Because they're essentially, some of these are parts of speech for each individual one. So that's the first place I would look. And one thing I would say is, if we go, sorry, we're gonna have to go back to your presentation where you talk about the flow chart, and if we scroll up right here. So one comment I want to make before explaining the rest of my thoughts is that when you're using the Stanford parser, you can choose the structure of the outputs, right? So you have words and tags, pen, and type dependencies. So I recommend, if you're finding one of them not useful at all and you have to program around them, just don't output them, right? You only have to output one thing. And that one thing that's most useful, like you said, is type dependencies, is going to be where a lot of the gold is here. Now, the other thing that you were saying, which you're dead accurate on, is that the Jython script, the person that authored that repo built a whole suite of tools that are directly applicable for this problem. So one of the reasons why other people using the Jython interpretation were able to get the shortest path is that there is an actual function that returns the shortest path between two different tokens or nodes in the tree. So this immediately gets you closer to what you want. It's still not as easy as saying, give me the path between these, because what you'll notice is when you run that, you have to say what you want the path between. So you have to define the two things you want to connect. So you might automatically be thinking, okay, I think the way we could do that right is we have a list of drugs and genes, and we can say, here's where the token location is in the final parse. So there's a little bit of wrangling that has to go into choosing what to connect in a programmatic fashion. But taking a step back at the higher level, that's why I recommended the Jython library, because it gives you that automatically. And again, what that will do is, for every sentence you're parsing, if you say, I want to connect these two different nodes, it will give you the shortest path between them. And not only will it give you the shortest path, it will actually give you something very close to the actual bracketed structure in D in the figure that you were showing. So if we scroll down to the figure, right there, perfect. So this is the challenge, right? Is you have a sentence A, and you guys have gotten to B and, well, not C yet. You've gotten to B, where you have the tree correctly parsed. The question then is, how do you get C and how do you get D from B? And this is what this Jython repo did. Whoever programmed it, really was doing quite a bit of interesting work. is they are using what appears to be a pretty simple traversal algorithm that essentially says, going from this node to this node, how do we connect them? What is the path, the shortest path between them? And so they take B's tree structure, and then they're able to get C. And then from C, you can also automatically extract D from that, because what it will print out is exactly what's in D, is it will give you the type and the linkage between the two. So that's why Gython is really useful in this case. And that's why it's worth the bit of hassle to set up if you are struggling to get C. Now, obviously, you don't need Gython to get C and D, right? Like there's clearly whatever code is working in Gython, you can run something very similar for C to get C and D. But I think that by far the quickest way to just move forward is by using that Gython repo. So that's what I would say is the disconnect right now, like you clearly have a great idea of what you need to get. And that's the most important piece, right? Conceptualizing where do we want to end up and where did we start? It's just filling in this gap right here. And your current bottleneck is the output that you get from Stanford Parser by default is not going to give you the shortest path. And on top of that, it's not going to put it into a data artifact like in D, right? So that's why I would recommend taking Gython and trying to get that up and running, at least one person on your team, because that way you can use it to extract this almost automatically. Now, if that's still a bottleneck where using Gython is difficult and you're finding that this is really where you're spending all of your time and it's getting very frustrating and you're not moving forwards, then again, we can use the original data set and just continue with the machine learning. And that slots very cleanly into the EBC repo, right? When you take their dependency matrix. But again, I would recommend trying to push on this and see if you can get Gython working, because it'll be a very good kind of story to tell and explanation and piece of code that you can kind of author if you're able to connect these pieces. But that's where the core disconnect is if you're just using the Java interpretation of the Stanford parser, getting C is difficult because you have to write your own code to connect these two nodes. Gython will do that automatically and give you printout that looks basically like D with a little extra massaging.
Okay. Yeah, that's definitely the missing piece. I think a challenge when you're working in a group is different people. So for example, for this module 2 script, I was in charge of all this. And then someone wrote the conversion from the Stanford parser output to this matrix. And I didn't realize that there wasn't enough signal to create that. And there might be some inherent flaw in this matrix. So I think that was just the missing link in trying to get it run correctly.
Absolutely. This can be a big challenge. If we go back up to your matrix, one of the main skills you want to learn is not necessarily using other libraries. That's kind of just expected, right? Okay, you just put it in EBC, good, fine. But something that's very hard to develop is the intuition as to whether or not this is reflecting what you expected, right? So one of the ways you could see it is a mod an actual path that can connect a drug and a gene? So not really, like it would be surprising if that was the case, because I don't see how that could come about from a sentence. But that's something that's really easy to gloss over, right? Because we see output here. It's of the right dimensionality, but how would you know? And developing that intuition is what you want to kind of portray in an interview situation where you have a good feel for how data should or should not appear, even if you're not a domain expert in it, right? That you can get familiarized with this kind of thing. And so hopefully this helps build kind of or reinforce this idea. And that's what you want to double check is every time you're creating a data artifact like this, just take a second and check a cell out, right? Here it's, we have an indicator 1 for prep such as, and you want to ask yourself, where does that occur? Does that make sense in my head? And sometimes the answer might be yes, sometimes it might be no, but we also see 2 here in this matrix, right? Connecting the second row to the furthest right. So these are things that you want to ask yourself, what is that reflecting? Is this the same structure as what we saw in the paper? And if the answer is no, it doesn't necessarily mean you're wrong, but you might want to double check, right? You might just want to ask yourself, is this sensible? Can I validate this any further? So that's what I would say is with this kind of data artifact, you can see a couple suspicious things that don't necessarily mean you're absolutely wrong. But I think in this case, there's just a disconnect between the way these columns were generated. And that's because there's a difference between what the paper put in the columns and what the Stanford parser outputs by default. So just trying to connect those two will push you along further, and continue to reach out, because again, you guys did a really fantastic job contextualizing the problem. This is also one of the main skills you want to develop, is if there's an issue, communicating what that issue is to people who might be able to help with the fix. And you just did a great job of giving exactly the information needed to try and figure out what was going on. So hopefully that gave you a couple foundational things to try and check out and just see. But that's where I would begin with. And again, just let us know if you're continuing to struggle to translate into these specific column syntax that is required to get EBC to run.
So if this doesn't have enough information and signal, so like what is the actual matrix in the research paper? Because I assume that the actual 2D matrix will be able to represent this shortest path, correct? Or...
Yeah, so essentially in D, so D is defining a connection between the drug and the gene. So if you look at D, we don't see a gene and we don't see a drug name, right? So D is the actual connection. It's the linguistic relationship between the drug and the gene without referencing the exact drug and the exact gene. So if you didn't see C above it, you would not know what drug and gene are being talked about in D. You would only know the nature of the connection. So what the actual machine learning requires is D is the shortest path parse of one sentence, right? So you are going to have hundreds of thousands of sentences eventually that contain both a drug and a gene. So that will result in potentially hundreds of thousands of paths that connect the drug and the gene. So each one of those paths, you're going to get a list of the unique paths that came about from the Stanford parser. And D is one such path. So this forms one column in your dependency path matrix. The idea is you're trying to find every other sentence that contains this path, right? So this might be a very rare path because, again, the main point they make in the paper is sparsity. Very rarely does a path connect multiple drug gene pairs. What's more common is the meaning of this path is very common, right? So just because this path has a specific linguistic styling does not mean that another path will not reflect the same meaning. It's just that other path might have a slightly different word order or a slightly different adjective, right, that describes something. So that's what the structure is trying to say, is you're trying to find every single possible connection between drugs and genes in your data. Every possible connection, you'll then take every unique one, right? You'll basically create a set of possible connections. That set of possible connections forms each column in the dependency path matrix. Then each row is, as you, I think, already correctly understand, is just a drug and a gene. And then the indicators say, is this drug and gene actually linked via this dependency path? And what you'll find is certain dependency paths link multiple times to different drug and gene sets. And certain drug and gene sets have multiple ways of being linked in the literature. So that's what the machine learning is trying to do, is this D expression, right? It has a meaning to it. There's a biological essence to what this is trying to convey that might be hard to abstract from just the words themselves. What the machine learning does is it tries to figure out, what is the meaning of D? And is there an alternative way of phrasing the same meaning or idea linguistically? And then after many iterations in convergence, this 2015 paper showed, yes, there is, right? We can actually abstract away the meaning of these dependency paths. And even though we're faced with severe sparsity, we can in fact recover something useful, even if the paths themselves are slightly different every time, right? Because that's what computers struggle with, is trying to infer semantic meaning. What they're very good at is crunching many numbers in a row, right? You're doing a lot of different computations. But if there are slight differences in the path itself, we need to find a way to generalize. So does that help you understand kind of the structuring of the dependency path matrix?
For sure. And the lengths of the column, the lengths of the paths can vary, right? Between each column.
Exactly, right? So some paths might be very complicated and some paths might be incredibly short, right? The drug and the gene might be one word of separation between them. So in that case, the shortest path would just have those three nodes, right? The drug, the gene, and the word in between them. But sometimes you need further context. So this path is a little bit longer, right? Because we see the word agent, right? Or well, we see exposure as an agent, part of speech tag. So in this case, the drug and the gene weren't directly next to each other. We saw expression getting mapped to the gene and exposure getting mapped to the drug, right? That's what this sort of shortest path in C is telling us. And so there's no guarantee what the length of the path may be, But that's part of the innovation of this machine learning is paths may be of varying lengths, but still talking about the same meaning. So is there an alternative sort of compressed way of reflecting the same relationship in general? So yeah, that's a great point, right? The paths might be of varying lengths. And also the varying lengths are going to depend on the way you choose to extract them from, Jython or Stanford Parser, whatever it is you use. But that's a good point. Yep.
Okay. And is the matrix what we're going to feed into the EBC algorithm?
Yeah.
And
So
Mhm.
Oh, go ahead. Sorry.
Oh, sorry. I was just confused if the EBC algorithm, after we got this consolidated matrix, it will essentially find clusters that are significant within this matrix. Is that what it does?
Exactly right. So because you have this indicator matrix telling you what paths connect what drug and gene pairs, it will be able to do bi-clustering, right? So figuring out clustering on the row and the column axes. And what that will be able to tell you is a particular drug gene pair a unanimous relationship, right? So remember the blue bars that you broke down so cleanly on that dendrogram, that probability?
Yes.
Yes. So those probabilities apply to a particular drug gene pair, right? And what we're trying to ask is, what are the odds that this should be a consensus relationship, right? So in that sense, what we're asking is, how frequently does this occur, right? And are there ways in which it co-clusters with consensus relationships? So that's what we're doing when we seed, right, with actual gold standard data, is we say, because DrugBank contains these relationships, right? And because these relationships are co-clustering with this new drug gene pair, odds are we're recovering something useful about the generalizability of that signal. So that's clustering on one axis. Clustering on the other axis is saying, okay, what are the different ways in which we can relate drugs and genes? So we saw inhibition, right? We're seeing increased expression here, right? That's another way. So what the dendrogram is trying to do for the clustering is say, of all these dependency paths, are there common themes of connection between drugs and genes? You can infer all of this. This is the coolest part about the machine learning, right? You can infer both kinds of relationships with just that indicator matrix because it's relying on the idea of semantic similarity, right? Are certain dependency paths connecting similar drugs and genes, and are drugs and genes connected by similar dependency paths? So it goes in both directions. That's what the bi-clustering part is it's trying to cluster rows and columns simultaneously. So that's how you get this landscape of connections, is it's saying, look, we have hundreds of thousands of different paths like D, right? And they all are potentially discussing a very limited set of themes. So if you remember the dendrogram, there were only 20 some clusters, right? And those 20 some clusters describe all hundreds of thousands of these paths in D. The reason being is these dependency paths have many different themes that keep occurring over and over again. So increased expression is one such theme, right? That can be one cluster, is increasing the expression. So there are an infinite number of ways to talk about increased expression, but this is just one of those unique ways. We hope that machine learning can generalize and say, here are all of the paths that are talking about this same idea. So that's clustering on the column axis, right? Trying to figure out what are the different themes of dependency paths in our data. Does that make sense?
So essentially, if the only way the machine learning algorithm knows that if two dependency paths tend to be clustered together is the indicators within that matrix.
That's exactly right. That's exactly right. So if two dependency paths are connecting very similar sets of drugs and genes, the machine learning makes an assumption that they're related in some way. And this makes sense.
But how did? Oh, sorry.
Oh no, go ahead. Go ahead. Ask your question.
It's because how does the algorithm know if two genes are similar to each other? If where does that information or signal come from, essentially?
Well, it doesn't know if two genes are similar to each other necessarily. What it can say is you have a drug and a gene pair, right? And let's say these are connected by some set of dependency paths. Well, if that same set of dependency paths also connects a different drug gene pair, odds are the drug and gene pairs are related in some fashion, right? Maybe they're very different genes and very different drugs, but the way in which they're related to each other is very similar. So that's how the machine learning infers whether or not two dependency paths mean something similar, is if they consistently connect drug and gene pairs over and over again. So that's part of the inference, is it tries to see, of all of the things that are connected, what is the frequency of those connections and what sets of things are connected by two different dependency paths. So it can be a little bit confusing to think about how these things converge, but you're exactly right. At the end of the day, all the information we have are these indicators, right, of whether or not a particular drug gene pair is connected by a particular dependency path. So there's only really two different things to consider, right? Which dependency paths co-cluster and which drug gene pairs co-cluster. And from those two sets of co-clustering, we're able to get the final probability of being a consensus drug gene pair. And we're also able to get these clusters in the overall dendrogram landscape. And those clusters arise from this phenomenon, right? What paths connect which drug and gene pairs? So this is why, I highly recommend, if it's very abstract to think about, but revisit the figure in the paper that shows the clustering along the column and row axes and talks about the different types of clustering that are seen for that example in the figure. And if you don't know what I'm talking about, it's that figure, it's the heat map, right? That shows kind of the orange-red connections between different column sets. And so if you happen to have it open, we might just want to look at that real quick, just so I can describe. I'm glad that you have this handy right here. Perfect.
Yep.
So we see here, right, that we're forming different clusters that say substrates, inducers, inhibitors. So what this means is that we're actually generalizing the types of dependency paths. The way we're generalizing is by seeing what drug gene pairs are connected by those dependency paths. So again, I know that this can be a lot to wrap your head around. It certainly took me a long time to figure out what is going on with the nature of these clusterings, but this is where you want to spend the majority of your time, because again, when you eventually talk about this in an interview situation, this is going to be really interesting to talk about co-clustering and the intuition behind generating row and column clusters. So, you really want to take a look at, if we see what the inverted axis is, we can see these are dependency paths that are connecting things, right? And when we see these dependency paths, then we're able to generalize what are the clusters of dependency paths here. What dependency paths are connecting very similar drug gene pairs over and over again? So that's what you want to take a look for, right? You want to try and figure out, where do these clusters come about? Like, what information is being used? At the end of the day, it's just the indicator. So you know that there's only kind of two directions you can look at. Does that help start, get you thinking about what to pay attention to?
So in these more dense areas, does it mean that this dependency relation essentially usually connect between these substrates? Is that what it means?
Yeah, exactly, right. So the darker it is, the more weight or emphasis put there. And this is also can be a misleading figure, because we see this is a smaller matrix. So if we scroll down to the label or caption of the figure, scroll up a little bit. Yep. So we see that this is just one gene and drug pairs, right? So this is drugs and then this gene, all the pairs that exist there. So this is just a heat map reflecting the different kinds of relationships with that particular gene. And we see all the different ways in which that gene can interact with other drugs. And then, like you said, the heat map shows the emphasis or weight put on that particular kind of connection. So there's a lot to dissect in this figure. And actually, I'm glad you bring it up, because this is going to be a big part of the EBC material that I send to you guys to help you try and get more of an intuition for this, because this, I think, is one of the more confusing ideas of the project. So the engineering part that's the hardest is extracting the paths. That's what your team is currently experiencing that bottleneck in. This, to me, is potentially the hardest idea to wrap your head around if you haven't seen this kind of math before, right? This kind of bi-clustering idea, and how you go from just indicators to all of a sudden intuitive clusters, right, of different dependency paths. But hopefully this figure, if you sit and really ask yourself, where does each piece of this come from? I would recommend actually you do the same thing you did with that dendrogram and just say, try and map out what are the different axes at play here and where did these clusters come about? That, if you start to think about that, and then hopefully the pre-recorded material I sort of show you will help connect those two dots, because this is a super important idea. I'm glad we're spending some time on this.
Okay.
Cool. Yeah, no, these are all great points. I think this is a confusing section for sure, and this is also the one that we want to spend more time on understanding because this is at the heart of what the machine learning was designed to do in this overall pipeline.
Was this more is this supervised learning in that the indicators, the labels, or is the clustering more unsupervised?
Yeah, that's a really great question. So there's only one, so there's an unsupervised step at the beginning, right? Where you're running iterations. The indicators are not supervised labels. It's very easy to
Oh.
think why they would be supervised, right? Because we're assigning an indicator label. But the actual supervisors are the ground truth relationships that exist in DrugBank. So this is an important idea to understand. The way we know about the quality, right? The scoring of a particular run comes from how frequently something co-clusters with a ground truth relationship from DrugBank. So if you remember in the EBC algorithm, you have a set of seeded labels, right? That are coming from, does this particular drug and gene exist in DrugBank? So that is the supervised signal that says, here are some true relationships. Now, the way we evaluate the algorithm is by saying, how frequently do we recover these true relationships? And what co-clusters with these true relationships? Does that make sense? Where the supervised data comes from?
Yeah, I think I can just read up more about it in this paper, and I hope it'll start to make more sense to me.
Okay, cool. That's a really good question, right? Is what is supervised and unsupervised about it? And you'll see when they describe EBC, they talk about an unsupervised step and then a supervised step. And the unsupervised step deals with the indicators and it, kind of runs its iterations. The supervised step injects ground truth knowledge that is sourced from DrugBank. And that ground truth knowledge is, does a drug gene pair occur in DrugBank, right? So if it's a known relationship in DrugBank, we can use that information to evaluate how good is our algorithm. The way we do this is by saying, how often does the algorithm recover this ground truth relationship, right? And if it is consistently recovering a ground truth relationship, we feel confident that it's actually learning something that is truly a consensus relationship. Then the other thing we can do is say what co-clusters with the ground truths, right? And if you run that enough times, you can generate new relationships. So that's a really important point. I think that we don't have time to dig any deeper, but thank you for bringing that up because that's something that we all want to deeply think about is what is the unsupervised step and what is the supervised step in EBC? And then that's why drawing these diagrams is so important because you can understand where do you inject the ground truth data, right? You have an indicator matrix and that's the first component, but then we're actually taking DrugBank relationships and injecting them into the algorithm itself. And if you plot out and make a diagram for the algorithm, you may remember Kwan's team kind of sketched out the overall diagram. I recommend revisiting that recording and trying to make your own to help conceptualize what goes into this algorithm and where does the data come from. And I think that you're very close to kind of feeling like it's all connecting, but like you said, a reread of the paper is always good. And you'll notice you're constantly discovering new things when you reread it, right? Because your experience helps you just kind of understand certain components and then talking through with the rest of your team and me and everybody else can help reframe your perspective when you read through. So it's always good, to, especially in a project like this, every once in a while, periodically reread because you'll begin to discover new things that finally click. And this is hopefully one of those things that after talking with me today, after rereading, it finally clicks kind of what the overall source of signal is. That's really what we want to think about, right? Where is the signal coming from in all of this? And I think you did a great job of bringing out all of the dynamics that surround that question. So thank you for, doing a deeper dive on that.
Yep, that's really cool. Thank you so much. That helps.
Absolutely.
A lot. Yep.
Cool. So I know we're running over time a little bit. Are there any other questions? Thanks guys for sticking on a little bit longer than usual. Glad to answer questions though. I believe I had, let me just check my schedule real quick. I do have some extra time right now if anybody has further questions.
I think it was just that module. If no one else have any question, it was that modular question about the one I forwarded to you, I guess.
Yes.
I mean that's all I have.
Cool.
If
so if we just
no one else have any question.
Okay, cool. Yeah, that's great. So just before we talk about the repo structure, anybody else with conceptual questions? Yeah, that's a, and just before we talk about the repo structure, Matthew, I just want to further reiterate in interview situations, a question I ask often, and I have been asked in the past, is exactly what Matthew and I were just talking about, which is what is the signal that is fueling your machine learning? And why does that make intuitive sense or interpretability aspects of that piece? So you want to be able to say, how are we actually learning? What are we learning from? And why do we assume that's a good set to learn something from? And so these are the types of qualitative questions that you will get asked all the time. And you want to be able to say exactly what the motivation was and how the process is learning from data. Because often what has happened in the past when I've been interviewing people is they have the toolkit down, they're proficient Python, R programmers, they know the algorithm names, they can talk about their experience and the metrics. But when you ask, what are you actually learning from? And why did you use this data to learn this particular problem? The entire interpretation kind of breaks down. So it's so important to frame and motivate your machine learning, not just be able to execute the toolkits, because again, that's far more common for people to be able to say, I'm proficient in Python programming, I ran this, I use this model, this library, et cetera. That's all great. It's very necessary. And we're building kind of experience with some of those tools as well. But more often than not, in the screening component of those types of interviews, that's the kind of thing we talk about is, do you understand why you were asked to do machine learning in the first place and how you're actually finding and recovering a signal and why that would be a signal in the first place? So yeah, I just want to reiterate that and just be thinking about those concepts. But moving on, if there are no other questions for repo structure, I think, Matthew, what you were talking about makes complete sense to me. So for those of you that haven't seen that in the forum, Matthew is talking. Do you want to just show again your screen, Matthew, if that's easiest?
Yep.
Might be cool.
Um,
Yeah, so you just want to walk us through. I mean, I think it's pretty self-explanatory looking at the screenshot, but you just want to explain kind of how you currently have this structured.
yeah, of course. So far, I followed or my group followed the utilities function advice that you gave, and that's been very helpful in our workflows. But if you see, for example, we want to implement the EBC algorithm, let's say here, if we put in this script, this EBC application script inside there, you can just do import. You would be able to do from matrix import whatever class object or a function, because there's a matrix.py within this directory. But if you put it outside, you would have to do import. You have to do import sys, which is the system Python library, and you need to manually add the path, which I've always found not very. It's too verbose to be efficient. And I was just wondering what was like the best way, because I really don't like writing everything in one script, and it gets really hard to track. And usually the paths I like to keep within, for example, within, for example, a class, and then you put it inside the constructor. And then you can just load it in from all the other modules so that you don't repeat yourself every time you create a module and like repository. And yeah, I just keep all the paths in one place and refer to that script. But as you build bigger and bigger applications, I think when you the best software development practices probably wouldn't make it so it will have a lot of connections between each other, the scripts. And I was just kind of wondering, because I have not been exposed to the best way of doing this, what would the best way to do this is, like for example, like trying to run this EBC algorithm repo from like a consolidated place that may be from like another directory without having to go through all the sys stuff.
Yeah,
I'm not sure if what I'm saying makes sense, but yeah, that was my attempt at explaining it.
No, you did a great job. It's a fantastic question. Again, it's one of those murky answers, right? Where there's no right way necessarily. There are some best practices. So I think that what you're doing is totally fine, right? It makes sense. And if this is working for you, it works. I think one of the best places to start when asking yourself how to frame this is by looking at other repositories, right? So we are actually looking, you have it loaded in on the left. If we go to the EBC repo, we can see the way they structure their code. And they're doing something very similar, right? Which is you have a main directory, and then within that main directory, your Py files are all accessible from that root directory, right? And this is the way that a lot of smaller repositories tend to do it. And then, like you said, as you scale out, you might need even more organization. And at that point, the question becomes, do you create a separate library, right, for a set of functions, or do you put it all in one? And that just comes down to personal preference, I think. I like to work in this way that EBC is currently structured, where every Py file is accessible from one directory. And if you have so many Py files that it becomes unmanageable, it probably reflects the fact that you want to refactor your code to put more things inside the same file. So you want to break your Py files down into kind of one task, right? One overall goal. And that's what they do with the EBC repo, is you can see each Py file corresponds to a very particular task. And if they had so many Py files that you couldn't read it, for example, right? Like you couldn't browse through, that would probably indicate they should refactor so that we have code that looks like what we're seeing on the margin. So this is what I would recommend doing, like you're saying, Matthew, is keeping everything accessible from the same level of directory to avoid multiple different directories where you have to source in, right? And use that syscall like you were saying. It is up to personal preference if you prefer to work that way and keep things separated into different directories. But typically for me, it's kind of a litmus test for whether or not I'm organizing my code correctly, is if it gets so messy and tangled that a situation like we're looking at in the EBC repo no longer works, it's probably on me to refactor. And what can happen is if you just accumulate a bunch of code in one script, that's the opposite end of the spectrum, where that's also terrible. And that's what you're saying, Matthew, is, it's bad and it feels bad and it's hard to navigate if everything is contained in a single Python script or notebook. So the middle ground is somewhere like what we're looking at in the EBC repo, and it's kind of what your group is converging towards, Matthew. So I definitely think that's a great approach. And if it's working, definitely keep going. So hopefully that's kind of useful. But yeah, I think that that's a great way to approach this organization.
How did they import EBC, even though they're like in the forward directory? Because EBC is like one level above it, right?
Yes, if we scroll up. So it's if you scroll up, so they're just taking. So we're in the test directory, right?
Yep.
If you collapse
We're
the
in
test directory. Yeah. So this typically will work out of the box. Have you tried to do something similar and it just didn't work for you, where you import to a directory above? Or import from a directory above, sorry.
Yeah, it's always confused me because I think you need to put init.pys at particular places for it to work.
Yeah, exactly.
I've tried to read the documentation of modules in Python, but it should just work right out of the box. Is that what you're saying? If it's like one level above it?
Well, you bring up a very important point, right? Because this is initialized as a Python module, it's actually able to access the right places from what I understand. So I think that you see here where it's calling.
Oh,
yeah.
Is this, you have to do this, then it works?
Yeah. So this is a really good case study for if you're also confused, and this is something that continues to confuse me, right? This is a hard thing to just get used to if you don't do it often, is take a look at the EBC repo and see what their chain of calls is to initpy and the import statements. And if you want to really extend the engineering here, a great way to add something to your resume and portfolio is if you build a Python library yourself. So this is something all the time that we use as a question to screen people out is, have you actually developed your own package in R? Because we work more in R in my group. And you have to interact with questions like this, right? Is how do you actually import between multiple files? And that can get really confusing if you don't have a reference point. I think this is a really good reference point because it's not so complicated, right? Like it's really only a couple files with this kind of one nested structure, but this is a really good way. They have an init right here. And then if you open up tests again, right? So
unit tests are
these are all their different tests, right? And then they're importing here. And that's how they're able to get this to work by just calling the reference from EBC, right? From EBC, import EBC. So take a look at this and just try and tinker with it, right? Because this is something that's, you can, clone, you can create a duplicate copy and play around and try and break. And I recommend this for anybody that's trying to actually be a machine learning engineer, because inevitably you will get asked, have you written your own library or package? In R, it's really more of a package is the nomenclature, but it's a pretty important question because it shows that you actually have organized code at more of the meta level instead of just done ad hoc programming. And that's really important if you're trying to contribute to a team, is to be able to write code in this style. So that's a really great point. Thanks for bringing it up, Matthew.
Oh, okay. Last point. How do you run this unit test over here? Do you have to go to the terminal and you run unit test module, and then it would essentially, you can test if all these pass?
Yeah, exactly. So that you basically run it like a Python script. So the testing libraries in R and Python are a little bit different. In R, there's that's one of the reasons I prefer R. To me, it's a little bit more sensible. The way in which R does its testing suites, but it's probably just because I'm less familiar with Python test suites. But yeah, in the simplest instantiation, you just basically run this as if it were any random script. But because you're importing unit test and it's defining what the test cases are, it will be able to tell you whether or not it passes. So that's what this is doing, right? If we scroll all the way to the bottom, keep going, you see these assertions that happen at the bottom. These are the kind of the equivalent logic pieces where you say, can we see if this assertion holds? If it does hold, then the test is passing. So testing is also a really important component towards package design and just in general when you're contributing to a team. And this is one of those aspects where data scientists often fall short, myself included, where software engineers are taught to write tests from the very beginning, right? It's a critical component towards their jobs. Data scientists and machine learning engineers often write their first test when they get their first job as a data scientist or machine learning engineer. So you don't want to get caught or blindsided, right, with what is testing, how do you write one? I think this is a pretty straightforward test example. So again, check the EBC repo out and ask yourself, what's different about this piece of code versus the code that I am writing for my project? Well, of course, it's a module, right? But on top of that, you see the init pies are creating an initialization for the library upon the import call. And on top of that, there's a test suite that allows you to check to make sure your code is actually passing. And so tests can be as simple as, does a piece of data exist? But they can get fairly complicated, right? Does it fall within a confidence interval of expectations, or et cetera, et cetera?
Oh,
so
wow.
check, yeah, exactly, right? But all of it builds from the same set of ideas. So for those of you who, again, want that more technical role as a data scientist or machine learning engineer, I would definitely try and get familiar with this as you begin to develop, because even if you don't end up writing your own tests for the STEMaway project, you can begin to get familiar with what tests look like in a repo that other people use. So this test suite is a big part of their validation and QC chain to ensure that this is ready to ship to people like us, right? This is how they know that they're confident in sharing this code. So writing a test suite is important if you want to share code to the rest of the world. And oftentimes when myself, or in the past when I've been interviewing, people will check out your portfolio and they will always look for, do you have a repo on GitHub, right? That's a pretty common way of just seeing what is this person all about. And if they see a repo that has a single Python notebook, they will say, okay, I'll check it out. But it's immediately demoralizing, because what that means is you basically just have a stream of consciousness piece of Python code. And in production, that's not what you want to see. It doesn't mean that that's wrong, right, or bad. And most of data science can be broken down into individual notebooks. But for something like this, you can immediately appreciate why they structured the repo the way they did, right? And so I recommend, again, exploring this, seeing what happens when you try and break the import statements, and ultimately trying to make something similar yourself, where you will turn your STEMaway code into its own library, right? And your STEMaway code might be the Python preprocessing, right? That filters for drug and gene names and outputs things. And that might be a really easy sort of starter, right? To be able to make your own library. And then you can test, can I import that code in a downstream notebook, for example? And if that works, you're well on your way to being an author of a repository that other people can use. That's really what you want to ask is, if somebody else uses this, how easy is it for them to use? And you'll notice EBC is very straightforward to use as an end user. So you might want to try and replicate that or mimic that, right, with your own code. But these are all great points. I'm glad you're bringing this up.
Yep, that's great. As an aspiring machine learning engineer, these are all stuff. I think you're hitting all the great points. So thank you for that.
Yeah, exactly. Sometimes it's hard to know what you would be expected to do during interviews and when you get your initial jobs, because again, it's not really part of school curriculums, right? And even in boot camps, it's really not an emphasis. And these are things that do truly matter when people evaluate the quality of candidates, as well as decide, you know, is somebody actually going to be a valuable contributor to their team? And I have seen people that are brilliant on the mathematical side and just really struggle to execute the programmatic elements of being a machine learning engineer. And it's because, you know, when they're in school, they're acing every assignment. And coincidentally, every assignment gives you a very clean, curated piece of data with, you know, a straightforward library to load, and that's that, right? And so we're trying to start from scratch, essentially. And this is why it's so great to see, you know, repositories like this, because they had to do something similar. And it gets you thinking about what do these things look like in when we try and polish them and share with the rest of the world. So that's a really important aspect towards being, a full, a glorified machine learning engineer. Yeah.
Yes, and they freeze it with the versioning and containers and stuff, right?
Exactly, right. That's another element to it. And it can be, I'm glad we're talking about this, right? Because it can be really difficult to keep track of all the tech involved, right? Because it's already a struggle to understand the modeling, to understand the math and the conceptualization. Then all of a sudden we're talking about unit tests, we're talking about Docker containers, we're talking about, you know, hosting on AWS. And all of that at once can be incredibly overwhelming. That's why I recommend taking the time to start doing it now, because you do not want to be in a situation where you feel overwhelmed at your first job just by trying to figure out what are these pieces of technology. You want to get the exposure. And of course, when you're starting out, people are understanding and they get you up to speed on documentation and you can see examples. But if you're not familiar already with what they look like, it can feel like a whole lot at once. And that was the case for me. Is the first time I was asked to serve a model in production, all of a sudden, you know, just because I knew how to build the model, I was in the dark completely, right? And I was very stressed and overwhelmed and struggled to actually get that model into production. And the gap was because I didn't do things like this. I didn't understand what testing looked like. I didn't understand what Docker was. I didn't understand what APIs were. And I also was kind of lacking in my Git knowledge, right? I hadn't contributed to a team repository. I'd only ever done it myself. And when you're using Git with just one person, it's just a linear commit stream, basically, right? So these are the things that really do matter when you're translating that knowledge into practice in a career. So yeah, I'm so glad you're bringing it up and just interested and engaged with these pieces, because inevitably, you know, you will be asked at some point to do it. The question is, how ready are you and familiar are you?
I was wondering if you're still planning on making the pre-recorded Docker material.
Yes.
If you had time, of course. Yeah.
Yes, absolutely. And so the thing that I'm going to wait for is Jillian, our DevOps engineer, is actually going to talk about Docker. And she is truly a bona fide Docker expert in that her career is built around kind of creating containers and manipulating them. I have only used Docker in the context of being a machine learning engineer serving a single model in production, which is a little bit more limited than her experience. Now, my experience might be very related to what you want to do. So what we'll do is we'll let her kind of give that webinar and then see what your questions are. Maybe that's enough for you to move forward, but I would suspect that you might want to see, okay, what does a machine learning model look like in Docker? And maybe she only covers the concepts of Docker, but doesn't show the machine learning portion. And then I'll create my pre-recorded material after she gets a chance to show you guys, you know, kind of the high level details of that. But she is truly, you know, an expert in those things. And I would defer to her on any points about Docker. And I you know, love it. I think it's an amazing tool, but sometimes you want somebody that truly has like made a living off of it to teach you. And then I can fill in those gaps for the machine learning aspects of it.
Okay, thank you so much.
Absolutely. Yeah. Cool. All right. So thank you for those that are still on. Hopefully some interesting things there to think about. And are there any further questions? Because I still have a little bit of time, but I know we're very much over the allotted hour for some of you. So just let me know if anybody has any questions. And as people filter out, I'll stick around. But otherwise, thanks for stopping by. And I'll talk to you all very soon.
if no one has any questions, I would like to ask, is there any good resources you recommend for self-learning? I know I've looked at the Coursera course for like machine learning, productionalizing machine learning
Mhm,
from deeplearning.ai. That looked pretty
mhm,
interesting.
mhm.
If there's any other resources you think would be great for I'm also trying to get AWS certified in that
Mhm, mhm,
that route as well.
mhm.
What we're just wondering if you think there's some things that will bring a lot of value for like aspiring machine learning engineers.
Yeah, it's a great question. I would need to just think a little bit. I have a collection of blog posts, and I don't know about the way you learn. For me, there have been multiple points where a single blog post, right, 3-pager, immediately makes something click, whereas a full course could not, cement something in my mind. So I have a list of
Wow.
blog posts related to Dockerization, productionizing models, APIs, et cetera, that really made me feel a lot more confident about that process. So I will look for them and then share them as kind of a compendium with kind of annotations as to what they are, similar to the learning resources, right, for STEMaway. And this is very cliched advice, but it's very true for me for sure. Is the best way to learn is just building a very simple machine learning model. So I'm talking, linear regression, right? Very simple data, open data, and make a Docker container that serves an API to predict new data. And this is going to seem simple on paper. And then when you start doing it, all these things will crop up that you're like, wow, I should really figure out how to seek these answers. And that's going to be the most useful, is if you're learning in conjunction with doing. And so I recommend, any open data sets that you've used before, something you're, at least a little bit familiar with, trying to build a machine learning model in either Python or R. Obviously, again, I use R. And, just taking that, building the simplest possible model, and then constructing an API. And in Python, again, Flask is super popular. In R, I use something called Plumber, which creates an API. And regardless of what direction you go, then just try and serve that in production. And by this, it can be as simple as creating a Docker container that has your API and just running it locally, right? You don't need to host it anywhere. That's a whole other layer. But if you can get those pieces clicking, you'll immediately feel a whole lot more confident about the entire process of containerization. So that's what I would recommend starting with, is just linear regression, simple data, or logistic regression, whatever it is, linear model, simple data set, and then create a Docker container that has Python in it, or whatever direction you choose to go, and then something that creates an API. And this, you're going to get into a rabbit hole of Flask blog posts, etc. And I can share my go-to tutorials and resources for that. And maybe they're helpful for you, but for some people, everybody learns differently. I can also compile some other video resources that have really built my understanding of these things over the past couple of years. So that's what I would recommend, is the easiest way to start getting into this stuff is just downloading Docker on your computer and just get going with a very simple model and something like Flask with Python or Plumber with R, regardless of which direction you want to go. And then that way you can take it piece by piece, build the model, then make sure your API works on your computer, then put your API in a Docker container, then spin your Docker container up and send a request to your API. That's the sort of the chain of command of trying to build it iteratively. And at that point, if you're able to do that, you're going to be able to slide right into a team that's using Docker for machine learning. You might need to learn more complicated aspects, or their Docker deployment might be more complicated. But if you nail the fundamentals, you're going to feel a lot better about, again, assimilating into a team that uses this tech. So that's my main recommendation. That was really the differentiator. Is I tried with blog posts and courses for Docker, and until I just had to build my first container with the model, nothing truly clicked. And the Docker documentation is quite good, but it's super extensive. It's one of those things that there are people that get paid to be Docker engineers, basically, right? Like their sole job
Right.
is maintaining containers. So there are so many things you can do with Docker. For us and for most people on this call, all you will ever need to do is put your model into production with a Docker container. That's probably going to be the extent of it. So I'd recommend reading kind of an overall intro on Docker's official website, but then not spending too much time stressing about all of these command line options and all of these, different things that clearly an experienced Docker engineer is going to be doing, but you won't ever have to do. So just stick with the model deployment for now.
Okay.
Cool. Yeah, it's a great question. I really think that, again, Docker and Git are the two main things that are becoming imperative to be a data scientist or machine learning engineer. And they're the two pieces of tech that people just don't know. coming out of school. And this has happened
Yeah.
time and time again. I see this, right? And that's why, hopefully using Git and using kind of versioning and inter-team communication has been pretty smooth for you so far. And you want to take it, piece by piece. And I think you guys are doing a great job of slowly accumulating more advanced technology that's scaffolding the rest of the project. But yeah, these
there
are
are
all great
also a
questions.
lot of MLOps like Databricks or Kubernetes or Kubeflow that make like you can kind of productionalize models and stage models. Do you recommend that I learn that and for example in like a Kaggle competition actually try to go through that MLOps entire life cycle of trying to do that using one of those tools? Do you think that would be a good idea?
I would never dissuade somebody from exploring tech, but here's what I would say is oftentimes tools that try and streamline things can perversely make it more complicated for you, right? Because they abstract away control over certain portions. This is definitely the case with myself. My bias with Git is I tried using a GUI for Git in the beginning, and that created a bunch of bad habits, and it destroyed my ability to fix mistakes and patch up emergencies and things like that. So similarly with DevOps, I think it's always best to actually take the hardest road at first, understand what each command is doing, and what happens when you make mistakes is the most important part. And then after you have that knowledge, then you can start making informed assessments of which of these tools, right, is going to be good for me. So oftentimes that's the problem is there are all of these new technologies and cloud providing platforms and all this stuff. And what happens is you just like stick with something and then use it because you get used to it. And you can't make an informed decision about why you're using that tool. I think that that's a pattern that has happened to me and a lot of colleagues that are more software engineers is if you just pick something that's more advanced and kind of fancier or cutting edge, sometimes that's bad for your overall development because you can't understand why you might want to use that. So that's what I would say on that front is take the time to actually do the hardest possible implementation. So this may be command line scripting, right? It's setting it up yourself, et cetera, et cetera. And when you start hitting bottlenecks and start seeing areas where it's confusing to you, that's when you start asking yourself, what would a tool need to provide to make this easier for me? Then you go and ask, okay, how can I branch out? How can I use these tools to make this experience a lot easier? That would be my recommendation.
So the hardest path that you're talking about is just doing everything through command line scripting, and that's enough for you to go through the entire lifecycle of DevOps. You just don't need these tools.
Well, you would eventually need these
containers.
tools. Yeah, you'll eventually need the tools, but it's just that there are so many options. It can be hard to understand what a tool is providing relative to another tool. So by command line scripting, I mean, before taking in any other technology, Docker obviously is most typically used via the command line, right? And so you essentially have a Docker file that defines a recipe for your container, and then you can use command line commands, right, to create that container, run it, and interact with it. And that's what I would recommend using it first is just locally on your computer, creating a Docker file that contains Python, your machine learning algorithm, the necessary data, et cetera, and then running it and interacting with it via the command line. Once you do that, you'll be way more informed as to what these other tools are even trying to do. And that way, when you go and see what they're purporting to offer to you, you can say, okay, that seems like something that would make this a whole lot easier. And this, again, this is the reason why I draw the parallel to Git, is that I used a lot of paid proprietary GUI tools for Git. And I just, again, learned a lot of bad habits. And I just didn't really know what was happening underneath the hood. And so if you create Docker containers via the command line, you'll have a much better idea of what's happening underneath the hood. And that way, you'll be a lot more informed when you start to integrate other tech stacks on top of that.
Okay, thank you so much. That helps a lot.
Great.
I think I was really confused with all these new stuff. It's exactly what you said.
Yeah.
I think you described myself.
Yeah.
It's funny.
Yeah, exactly. And I always recommend, you want to learn tech first in isolation, then in dependence. And what I mean by this, right, is learn Git on a toy example itself, right? Just two text files in two different branches, right? And then just merge and join and figure out how Git works. Then learn Docker with the simplest possible machine learning model, right? It's just linear regression. Then learn Flask without putting it in Docker, right? Just create an API itself. Then once you get each piece down, start to link them together. Use a fancier machine learning library, right, for your machine learning. Then use Flask inside of a Docker container. Then take your Docker container and put it on AWS after you know how AWS works with pre-existing containers. I think part of the challenge of machine learning today is you're drowning in options and everything depends on everything else, right? Is DevOps engineers need all of the SQL commands, all of the machine learning, all of the DevOps pieces to work in harmony. And people get stressed out because they try and learn everything in tandem. And this can actually have a very negative impact on your ability to do any of these things, because what it makes it feel like is everything is so complicated. So what you want to do is break it down to the simplest possible instantiation. So, when you're doing Docker, don't try and host it on AWS, just do it locally. APIs, don't put them in Docker yet, just make sure the API works on your computer and that's it. And that way you focus on one piece of tech at a time, instead of getting overwhelmed with trying to deploy a fancy machine learning model in Docker using Git all at the same time. That will be very counterproductive. So that's the other main advice I would give, is just break it down into each piece of tech on a very simple problem at first.
And another layer is using a GPU, right? From
Yes.
the cloud. Is that another?
Yes. And so the hardware aspects are also a place where people stumble, right? Instantiating CUDA, setting it up. Most of you are going to be lucky enough to actually have CUDA already installed, but it can be a real pain in the ass to try and get CUDA going when you build a system yourself or a cluster yourself. So I would recommend not, playing around with GPU models unless you have to, and learning them separately, right? This is part of the same idea. Is AWS has tons of GPU enabled clusters. So just use deep learning models on those clusters that are already provided, as opposed to trying to set it up yourself, because that can be a whole rabbit hole in and of itself, like you're saying, where oftentimes you're getting errors with the hardware and all of a sudden, is that a Docker problem? Is that a hardware problem? Is that a U problem? Who knows, right? And until you've worked with each piece independently, it's very difficult to answer those kinds of questions. So yeah, I would recommend, when you're starting all of this, building machine learning models that are just really simple linear models from either scikit-learn or an R. I use GlimNet all the time for regularized regressions. So, stick with something like that at first.
Okay, glad to know it's something everyone experiences.
Definitely. Yeah, these are all great questions. Thanks for bringing it up. Okay, cool. So I think with that, we will head out. Thanks everybody for listening, and thanks Matthew for providing all that great conversational foundation. And hopefully that was useful for you.
Yes, for sure. Thank you again.
All right, great. I'll talk to you guys soon then.